All right, so the last class of waves that we're going to be introducing here are called electromagnetic waves or light, and I'm sure you've come across that before in grade 9. But these waves are kind of magical because unlike the other ones that we introduced, the other mechanical waves we've introduced, electromagnetic waves don't require a medium. They're the only type of wave that can be transported through a vacuum or through outer space, whereas the other ones require all the particles in a wave to be able to communicate in order to transmit the energy of the wave. Okay, so electromagnetic, where does electro come from? Where does magnetic come from? Well, if you take a look at this mechanical wave here, this transverse wave, okay, it looks very similar to the light wave in the fact that light waves are actually transverse waves as well, okay, except the light wave is made by a charge. If you see this red line, imagine that's a positive charge going up and down. That positive charge is going to emanate an oscillating electric field. For those of you who were in physics last year when we did electricity, you would have barely remembered right now what an electric field is. But whenever you have a charged object in space, it generates a force on charges at a distance. It doesn't require a medium. Okay, so if I move the charge up and down, the electric field that it generates is also going to be changing its strength up and down. Okay, and so what we'll see here is the oscillating electric charge is generating an oscillating electric field. And something you're going to learn in the next unit is whenever you move a charge, right, you generate a perpendicular magnetic field. So this blue line is a magnetic field. So in light, you have an oscillating electric field and an oscillating magnetic field perpendicular to it. Okay, and that's what it looks like. Now, that oscillating electric field and magnetic field can interact with other particles that would interact with electric fields and magnetic fields as well. And that's how we sense light. Okay, so light is composed of an oscillating electric field that has an oscillating magnetic field associated with it. And the two oscillating fields are perpendicular to each other. That's important to know. And they propagate in space at the speed of light, roughly around 3 times 10 to the 8 meters per second in a vacuum. Okay, that's important for us to know. When we learn some other properties of light, when we talk about refraction, light can be slowed down, but in a vacuum, it travels at 3 times 10 to the 8 meters per second. Very important number to know. Okay, then electromagnetic waves are transverse, like I said, and they don't require a medium to transfer energy. The reason I have these 3 things down here is often you'll get a question that says, describe 3 important properties of light, okay, and these would be the 3 things that you have to talk about. Okay, so here's just another little video demonstration of the oscillating electric field. And at the peak of that oscillating electric field, you're getting perpendicular to it, the peak of the magnetic field. Okay, and the direction of the magnetic field you'll learn in the next unit when we talk about electricity. All right, so what kind of waves do we have? We have what's called the electromagnetic spectrum. I'm sure you've done a presentation on it in grade 8 or grade 9. But the electromagnetic spectrum is all the different frequencies and wavelengths associated with oscillating electric and magnetic fields, okay? And this little video that you're seeing over here starts from the longest wavelength going to the shortest wavelength. So the longest wavelength electromagnetic wave would be radio waves, okay, on the order of meters. And then after that, you have microwaves, infrared radiation, visible light, UV light, X-rays, and gamma rays. Gamma rays have the smallest wavelength, and what we should know from the wave equation, which looks like this, okay, is that if I rearrange this equation, okay, the wavelength of a wave is going to be inversely proportional to the frequency of the wave. Okay, so the greater the wavelength, the smaller the frequency. The smaller the wavelength, the greater the frequency. Okay, and that's what you see being represented here. That's really, really important. So long waves have low frequency. Short waves, like gamma rays, have very, very high frequencies. Okay, and then here is just another diagram. It's in the opposite direction, from long wavelength to short wavelength. Okay, but here's just the different regions of the electromagnetic spectrum put more visually for you guys. Okay, long waves have wavelengths on the order of kilometers. Okay, those are extremely long waves, all right? And that would be very, very low frequencies, okay? And then here's our radio waves on the order of 100 meters to meters. Our Wi-Fi that we use in our classroom, which changes, is on the edge of the microwave spectrum. So these are on like centimeters. Then you got your microwaves, which is like in millimeters or micrometers. And then you got infrared, which is between 10 to the minus 4 and 10 to the minus 6 meters. And then here's the Roy G. Biv, okay, that rainbow spectrum. Okay, what I said was Roy G. Biv, Roy G. Biv. This gives us an idea. Red, so that's red, that's orange, that's yellow, that's green, blue, indigo, and violet. Okay, that would be just going in the opposite way. Red, orange, yellow, green, blue, indigo, and violet. That looks blue to me, but that's violet. Okay, and that would be your visible spectrum. So going from highest wavelength to shortest wavelength. Okay, so this is your highest wavelength, shortest wavelength, lowest frequency, highest frequency. And this is a very important range that you have to remember. You actually have to remember the actual wavelength range of visible light. There's questions and you have to know it off by heart. So blue light, or the violet light, is going to be around 400 nanometers. Okay, and then red light is on the range of 700 nanometers. These are nanometer wavelengths, okay? And then if I apply the nanometer wavelengths and the speed of light into the wave equation, I can calculate the frequency, which is on the range of 10 to the 14 to 10 to the 15 hertz. That's pretty fast frequencies. Okay, now lower than that is going to be UV light, which has a smaller wavelength. It's between like 300 and 100 nanometers. UV light is much more powerful than visible light. We have diseases associated with that, cancer and things like that. X-rays are even more powerful, more energy carrying, okay? And they are much smaller. They're an order of magnitude smaller than UV light in terms of their wavelength. And then gamma rays are associated with nuclear rays and cause a lot of damage to humans, okay? So already I'm kind of giving you an idea that the higher the wavelength, the lower the energy. The lower the wavelength, the higher the energy. Sorry, it's just my dog. All right. And then how to calculate the energy of wavelengths of light. The energy is equal to Planck's constant, which is 6.64 times 10 to the minus 34 times 3 times 10 to the 8 meters per second divided by the wavelength, whatever the wavelength is. So let's just say wavelength is 400 times 10 to the minus 9 meters. If I put that together, I'd be able to calculate the energy in joules.